Now you can get relations as the solutions to your differential equations. Just because they don't pass a vertical line test doesn't mean that they're not eligible to be solutions. And you'll still get the usual constants and they'll be still families of curves. But a couple of things to note. We might need the chain rule and we might need the product rule if we are differentiating, say, powers of y with respect to x, or if we're differentiating terms that have x and y in them with respect to x. So these examples are nice and simple, but having looked at these, you should be able to extrapolate this method to other examples that are like this. Now, if we are differentiating y with respect to x, and y is some function of x, then if we then need to differentiate y squared, we're using the chain rule because we need to differentiate the global shape of this thing, which is to bring the 2 out the front and reduce the power down to 1. But then we also need to multiply by the chain part, and that's where the chain rule comes in. If y is a function of x, then we obviously need to multiply by dy dx, and we can just call that y dash. So we can tidy that up and say we get 2y y dash. Now, just to be really clear what this would look like, let's just do an example that might have a very simple function of x. Perhaps x is 5x plus 2, say. Now, if we had y squared, that would be 5x plus 2 all squared. Now, if we wanted to differentiate this thing with respect to x, we know that we need to use the chain rule. We bring the 2 out the front, we rewrite the function of x, in other words, y, and we drop the power down by 1. So we've got our 2, we've got y, and then we need to differentiate what's in the brackets, in other words, differentiate y, that's our y dash part, and also bring that out the front, or multiply the whole thing by that. So we've used this chain rule plenty of times, and this is just an example of how we can use it. Even if we don't know what the function of x is, we've got a basic rule. Now, we'd need to use the product rule if we're differentiating something like xy with respect to x. Now, this is just two things multiplied together, so the product rule tells us that we need to do this term multiplied by the derivative of this one with respect to x, and then add that to this term multiplied by the differentiation of this with respect to x. So vu dash plus uv dash, or the other way around. So it doesn't matter which way around you do this. If we say we need x multiplied by the derivative of y, now we're differentiating y with respect to x, so we could write dy dx. We're just going to write y dash, so it's tidy. But then we need to add y multiplied by the derivative of x. Now, if we differentiate x with respect to x, we just get 1. So there's probably no need to multiply that by 1, and this is our quite simple result. So that should help us actually differentiate the equation for a circle. Now, x squared plus y squared equals a squared, where a is greater than or equal to 0, is just a circle that's got its center at the origin and it's got a radius of a. Now, we haven't differentiated something like this with respect to x because in the past, we've only really differentiated functions or things that say y equals something, whether or not they actually pass a function test. So here, we need to just differentiate each term, one term at a time, including the right-hand side. And we need to show that each equation in the family of solution curves satisfies this differential equation, y dash equals negative x over y. Then we need to find the geometrical significance of this result. Okay, so differentiating one term at a time. If we differentiate x squared with respect to x, we just get 2x. And if we differentiate y squared with respect to x, well, we just did that. We need to use the chain rule, bring the 2 out the front, and we're going to get 2y, but we need to multiply by y dash. And if we differentiate a squared, which is just some number, with respect to x, we get nothing. So we get this. So now we just need to rearrange this and get it in this form. Well, straight away it jumps out at me that this one doesn't have 2's. We can divide all of the terms by 2, and it tidies up straight away. Then let's get this term on its own by subtracting x from both sides. And then let's get y dash by itself by dividing both sides by y. And we've done it. So we can put a little as required there to show that we've got there. So what is the geometrical significance of this? Well, to understand what's going on here, it might be helpful to sketch it. Now, if we take any point on this circle, let's call it a point P, and it's got an x value and a y value, then we can see that this distance here is going to be a, because that's our radius. So over here, this would be a. We've got a, and negative a. Well, what we've just found is that the derivative, now the derivative of this circle means, tell me the gradient of the tangent to the circle, anywhere I care to look. So it means that we can take any point on this circle P, no matter where it is, and we can say, what's the gradient of the circle right there? Or what is the gradient of the tangent to the circle right there? So if we look at this point here, it's a nice one, and say, well, what's the gradient right there? What we found is that the gradient of that line is negative x over y. Now the significance is that the x value here, if we just drop a line down to make a little right angled triangle, we can see that this length here, from here to here, is x. And this length here is y. So if we actually looked at the gradient of this radius that we've drawn, we would say that the gradient of the radius is rise over run, it's y over x. Now what do you notice about y over x and negative x over y? One is the negative reciprocal of the other, and what do we know about gradients that are negative reciprocals? They're perpendicular to each other. So this is a fact that we've learned before, but we haven't necessarily proven it. Well, we've just proven it now. We've proven that a radius to a circle and a tangent to a circle are actually at right angles to each other. So the significance is that the radius and tangent are perpendicular. And if you wanted to actually prove that, then you would just multiply the gradients together and get -1. In this example, we're differentiating a hyperbola, and we've got a squared as the constant, where a is greater than or equal to 0, and we're differentiating with respect to x. So let's just think about what we've done before. If we had a basic hyperbola, let's say we had xy equals a squared like this, and we wanted to rewrite it in a form we were familiar with, so that it's in terms of y. In the past, we've already learned how to differentiate this. The first step is to actually change it so that the powers of x are negative indices rather than having an x on the bottom of our fraction. And then we can find y dash by just bringing our negative out the front. We'll get negative a squared, and we drop the power down by 1, which can be written like that, or it can be written like this. Now, what we're being asked to do here is actually to keep it in a form xy equals a squared, and so that what we're going to get over here is actually going to have y in it. So we're basically comparing the result to what the formula for the actual function is in the first place. So let's just keep in mind what we get there when we actually go ahead and do this as we're being asked today. If we differentiate xy with respect to x, we need the product rule. So we say let's do x times the derivative of y with respect to x. So we're going to have x y dash, and then we're going to add the derivative of x, which is just 1, multiplied by y. And then if we differentiate the other side with respect, we just get 0. Now, rearranging this, we can easily put x y dash is equal to -y, just subtracting y from both sides. And then to get y dash by itself, we've got -y over x. Now, comparing the two results here, are they the same? This one actually has y in it. This one doesn't. So this is our new skill today. Now, if we actually compare this one, let's just go over here and think about it. If we subbed in what y is equal to, we can see that y is equal to a squared over x. We could convert this one into the other one by saying, all right, it's negative y, and y is a squared over x. And that tidies up to just give us negative a squared over x squared, which is exactly what we got when we did it the other way around. Now, I'm really just showing you these two methods so that you can reconcile what you already learnt to do with what we're doing today. And the difference is that we've actually incorporated the formula for y in our result for the derivative. So we can get rid of all of this part. This is something we knew how to do before, and focus on the new skill for today. Now, what is the geometrical significance of this result? Well, if we draw a hyperbola, and let's just, for simplicity's sake, look at the upper arm here in the first quadrant, then if xy is equal to a squared, then each x value multiplied by the corresponding y value on this curve equals a squared. So if we're now saying, well, what does this really mean? It means, what's the gradient on this curve at any point that I look at? Well, let's just choose a point here, xy. What we can see is that the gradient there is negative y over x. So drawing in a little line here of the gradient, we can see that it's minus, and it's definitely a negative gradient, y, yep, that's the y value, over x. Now, what's curious here is that this is actually the x value from here to here. So if I actually drew a line coming down this way, let's do it in another colour, wouldn't I say that the gradient of this line is y over x? But the gradient of this line is negative y over x. That means that this must be a little isosceles triangle. I know it doesn't look fantastic on my drawing. That's because it's quite a rough sketch and I've sort of got my head on the side while I've drawn it. But what we're saying is that this distance here is also x. Well, not to there, to here. And what we have here is a little isosceles triangle, which is a curious result, maybe not something that we've considered occurs underneath hyperbolas, but it clearly does. And so we're using the gradient to make inferences, I suppose, about those points x, y that are on the curves, and we really couldn't do that with our other version of the derivative.